In this next video, we're going to look at trig equations still, but you're going to notice these look a little bit different. In our last video, we didn't have any squares or cubes or anything like that. It was just, sine or tangent, cosine, whatever it is. Here, we're bringing in squares now. So how do we deal with things like this? So these kind of look like our quadratics. And you would use the techniques you would use for solving quadratics here as well. So one thing we're going to do here, and a good technique for quadratics, if you can do it, is to factor. So notice that you have a square and you also have a middle term and an end term. So this kind of looks like a regular trinomial, but with trig functions. So it's a little bit harder. It's not really a regular trinomial, but it kind of has that same structure. If you got rid of the trig part, right, it kind of looks like 2x squared plus x minus 1 equals 0. So it kind of has that same form, but instead of having x's, it's cosine x's. So one technique we can use for quadratics, although there's many, is to see if we can factor it. Now, not every trinomial is factorable, but it's a good place to start. This one does happen to be factorable. And it factors as 2 cosine x minus 1 times cosine x plus 1. Sometimes it helps to put this in a base form first. Oftentimes we use u's instead of x's here, which is a substitution technique. So you can use any variable you want, whatever is helpful for you to get that factored. And when you factor it, this factors into 2x minus 1, x plus 1, because you get that 2x squared, you get a positive 2x and a minus x to give you 1x, and then you get the minus 1. So if you're trying to factor a trig function, I would recommend either just changing it to x, or usually we use u's. So you'll see it look like this, 2u squared, which is a substitution technique to figure out what that base factorization is. And then you can bring back in the trig part. So I have that base factorization, but instead of x, it should be cosine x's instead. Now remember, your next step when you factor with quadratics is to set each piece equal to 0 and solve. So this factoring technique works when you have an equal 0 on the right side. So don't forget that piece. Again, we're relying on a lot of algebra that you should already remember. So when you're factoring, just keep in mind you do have to have equal 0 on the right side. As you're going through your notes too, feel free to add in any notes or comments as I'm talking. Sometimes I write the key things down, but if I say something that you're like, oh, I got to remember that, like remember equals 0 when factoring, write those in for yourself. So do whatever you need to do to help you remember these processes and kind of remember that algebra that, maybe you haven't seen it in a while, or some little techniques that, hopefully are coming back to you as we go through them. Now for each one, you're going to go ahead and solve for cosine x. So here, think about your regular solving techniques. I'm going to add 1 to both sides. And then I'm going to divide by 2. Notice that I'm okay to divide by 2 because the 2 is outside of the cosine function, right? It's not being plugged in. So that's a little bit different here than we saw in the last couple of examples. All right, so now I'm going to have to go through my cosine values here. And I'm going to just do one at a time. Going through my old notes. So, it's always good, particularly in math class, to stay organized and to, label everything, put dates on them for yourself, whatever helps. So here is our graph of the cosine function that we made, again, a few videos ago. And the period here is 2 pi. A little note too, if you ever forget, you can always, again, use Desmos. It's a great tool to help you visualize that graph again. And what I have here are the key cosine values between 0 and 2 pi. That tends to be the first period that we look at a lot of times for our functions. So I have those values right here for you. And what we're looking for first is 1/2. So I can see that we get 1/2 at pi over 3, and then also at 5 pi over 3. And then for the other one, we're looking at -1, and that occurs at just pi. Okay, so let me write those down. So for this one here, we know that x would be, what did we say? We said pi over 3 and 5 pi over 3. And then over here, we said that that works for x equals pi. Now, these are periodic with period 2 pi here, but notice that I just have an x here, so I don't really have to worry about solving anything extra. And our domain restriction is just between 0 and 2 pi. So I can actually avoid putting that extra piece in. Normally we write our final answers, right, with the period, so 2 pi n like this, right? So again, remember that that comes from the period here. But because we're only looking for our restricted domain here from 0 to 2 pi, this is only going to be relative really when n equals 0 in this case. If you try n equals 1 and try it at home, you'll see that it's too big. You're going to be adding an extra 2 pi there, so you're going to be over that initial restriction. So n equals 0 is the only one that we need. So there's really only 3 answers. Our answers are really just pi over 3, 5 pi over 3, and pi. It's a good habit to get used to writing the final answer in this format, just so you don't forget. When you don't have those domain restrictions, or if you have a domain restriction that's not just 0 to 2 pi, maybe you're going through a couple cycles of the function, it's a good idea to get used to writing this and remembering it. But again, because the restriction here is small, adding 2 pi is going to be too big. So if you try doing anything bigger with n equals 1 or so on, it's just not going to work. So that is our equation here. Let's do another example. And again, you do have your domain restriction. Here you have a square. Now I could try factoring here, but this one's a little bit different than the last one. Notice in the last one, kind of had that format of a square piece and then a middle term, right? Here, I don't have a middle term. I just have the square piece. I don't have a sine x. So for something like this, it may be a good idea to solve for sine squared. And then what we can use is the square root property and taking the square root of both sides. So here I'm going to add 1 to both sides. I'm going to divide by 4. Now think about how do you get rid of a square? You take the square root. So I'm going to take the square root of both sides. It is plus or minus here because you can't have negatives. We're not just restricted to the first quadrant. So sine x is equal to plus or minus the square root of 1/4. But the square root of 1/4 is just 1/2, right? Square root of 1 is 1, square root of 4 is 2. So we're looking at where is sine x positive or negative 1/2. Now I'm going to let you take out your chart again. Again, we've used the sine chart a few times already, but if you take out your sine chart again, you'll see, just to kind of make a note here, that sine x is equal to 1/2 when x is equal to pi over 6. And when it is also equal to 5 pi over 6, and it's equal to negative 1/2 when x is equal to, let's see, 7 pi over 6 and 11 pi over 6. Now, when you're looking at that sine chart, the one that we have that we did on the graphs of the sine and cosine functions goes from 0 to 2 pi. So you have all the values here. You also don't have anything being plugged in besides x. That's when it gets a little bit messy where you have extra work to do. But here, if it's just an x, you basically have your answers. Now, of course, if we didn't have a domain restriction, we would go ahead and add in that 2 pi n, right? Because the period of sine equals 2 pi. And same thing here. However, in this particular case, because you have the domain restriction, you really only need the values for n equals 0 here. If you try n equals 1, it's going to be too big. So the final answers in this particular case, again, just because you have that domain restriction, are going to be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those are the only values between 0 and less than 2 pi that will work for this equation. All right, let's do one more example in this video. I'll do a few more after too. For this one, I'm just trying to show you a bunch of different techniques. So I showed you some without squares in the first video and some harder ones where you had other numbers being plugged in besides just x. In this video, we're kind of focusing on how to deal with when you have squares instead. So we'll do one more of those. Okay, so here I have, again, a square, and I also have tangents as well, but I have a square here, so if you're thinking about this a little bit differently, I can't just kind of solve a regular equation. I'm going to try bringing everything to one side. So sometimes when you're kind of stuck and you're like, I don't know what to do, I can't really factor this yet, I don't know how to solve this, right? I don't want to take the square root yet. Bring everything to one side. You cannot divide both sides by tan x. So that's a technique that a lot of students try to do. They try to divide both sides by an x or something with an x, and it just doesn't work. You end up losing solutions. So what you want to do instead is you want to bring everything to one side. So I'm going to subtract that 3 tangent x to one side. And then I'm going to notice that both of these have tangent in them. So I'm going to go ahead and factor it out. And remember, this is being multiplied here. Not minus 3, minus 3, excuse me, not 1. I was going to run a 1 there by accident. Now this is factored and it's equal to 0. So we can actually use our first strategy by setting each term equal to 0. Now the first one's already solved. I can't really do anything else there. So I'm just going to solve the second equation and add 3 to both sides. I'm going to take that square root plus or minus. Now, one thing I want to know before I get back to tangent is that when you're solving for sine x, again, there's nothing being plugged in here. And we're looking at 0 to 2 pi. If you go to your sine chart, you're going to notice you're not ever going to see a root 3. And if you plug root 3 into your calculator, I bring my calculator up here. You get a value of about 1.73. Now remember the regular sine function. So this is not being tweaked, right? We're not multiplying or adding anything to it. It's just sine x. That regular sine function goes between -1 and 1. It's never going to hit 1.73 unless we apply some sort of shift or some tweaking to it, right? So this is not going to happen. So here's an example where this part has no solution, because our regular sine function, this is just the regular sine function, is between -1 and 1. So that part is going to have no solution here. And you can also see it by your chart. So if you look in your chart, or if you try graphing something like this, you'll notice that there's no intersection between these two values, or the left side and the value on the right side. Now for tangent x, there are two values that we do have here. Tangent x is equal to 0 when x is equal to 0, and when x is equal to pi. And again, I'll let you take out your charts for that. 0 is a pretty common value. So we do see that one as well occasionally. And you have that value of 0 on your initial tangent piece. I don't know if you have the value of pi there, but we have seen it in other examples. Or if you are stuck, you can use your unit circle to figure it out. You could use your calculator here, although here it's just 0, so it's fine. But you can try different values here. And you can think about that period for pi. So that period for tangent, excuse me. So the period here is pi for tangent. So on your chart, you do have the 0 value. And then if you think about that period being pi, if I add pi to it, 0 plus pi is pi. So that gives me the second value there as well. And remember that we're going between 0 and 2 pi here. So that's why we're doing more than one cycle for the tangent function. So you have more than just that initial answer here. Now, again, you can think of this, another way to do it is if you look at your initial tangent chart. Maybe I will bring it up for a second here. Right, so our initial tangent chart goes between negative pi over 2 and positive pi over 2. So it's not quite in the realm that we're looking, right? We're going from 0 to pi here, but I do see that value of 0 occurs at 0. So another thing that you can do if you're missing the pi factor is remember that, well, our value is 0 here, and then I can always add pi n because the period of tangent is pi. And then if you go through your different options, well, when n equals 0, I have x equals 0. And when n equals 1, I have x equals 0 plus pi times 1, which is pi. When I try n equals 2, it gets to be too big because I'm doing pi times 2, which is 2 pi, and we're outside the realm. This is strictly less than pi. So we can see our two answers right here, or again, you can also see them right here. So there's different ways to think of this. Just remember what your restricted domain is if you have one, and make sure you consider all values within it. So for me, probably the one I would have done was this, because I could see that 0 right away on my chart. And then I know the period is pi, and then I can circle through my different n values to see where I should stop there. So this problem has just two answers in this case, 0 and pi.